Definitely about to stir up the engineers with this one. So check this out. If you're a first or a second year apprentice, there's a pretty good likelihood that you're going to learn something about Kirchhoff's voltage law. Now, it sounds really fancy and complicated, but let me break it down for you in the simplest way possible. So there's a lot to dissect here, and I don't think I can talk about it all in a 3-minute video. There's 2 main points I'd like to drive home. Number 1 is the electromotive force in a circuit equals the voltage drop across all circuit components. And number 2, the algebraic sum of all voltages in a loop must equal 0. So how's that work? How do we add up a whole bunch of stuff and make it equal 0? Well, check this out. I got a schematic drawing right here where we got a DC power source and 3 resistors wired in series. When we add up the voltages, we have to make sure we're adding up going the same direction the whole way around the diagram. And whether or not it's going to be a negative or positive voltage is going to be dependent on what the polarity is as we enter that circuit component. So let's go ahead and tally this up. So we're going to start right here. We got positive 3 volts plus positive 4 volts plus positive 5 volts plus negative 12 volts. And if you tally all that up, we'll come to the figure of 0. Because that's basically saying 3 plus 4 plus 5 minus 12 equals 0, which is true. Basically, this is just a really fancy way of saying voltage doesn't disappear. Now, I realize we're talking about DC, but this works with AC too. You probably didn't even know that you knew this already, but you've probably seen it in the form of ET equals E1 plus E2 plus E3. Now, I'm not going to waste my time drawing up another schematic, but I got a demonstration set up, and I'm going to show you what that looks like in real life. So right here's my setup. Got this variable auto transformer courtesy of Stephen J. 120 volts. Steve, if you're watching this, thank you again. This will serve as our power source for the experiment. Here I have about 300 feet of extension cord coiled up, sitting right here on the workbench. Then I got a toaster plugged in. Got my Feniercy digital multimeter, which by the way, guys, if you want to snag one of these for yourself, you can click that link right there down below. Let's go ahead and take some readings then. Going to take a reading at the source, which is going to be the secondary terminals of the transformer. About 116. Now I'm going to very carefully check voltage at the load, which we'll just consider the end of the cord here to be the load. About 106. So we lost about 10 volts. Now, I'm going to check voltage across both of these conductors because you got to think, with 300 feet of cord coiled up, we got a whole lot of resistance across both circuit conductors. So, I'm going to check voltage from the power source to the neutral side of this plug. Got about 5 volts. And then I'm going to check voltage from this conductor at the source to this conductor at the load. Again, got about 5 volts. We read 116 volts at the power source. We read 106 volts at the load, which means we lost 10 volts. Where'd they go? Well, they were across both conductors. So we had 5 volts across the white conductor from start to finish, and we had 5 volts across the black conductor from start to finish. And if we go ahead and tally them all up, 106 plus 5 plus 5 equals 116.